Hello everyone, welcome back to my channel Chemistry for Fun. So as we have discussed, today we are going to start with our general organic chemistry from Himanshu Pandey. So this is our GOC, general organic chemistry from Himanshu Pandey. Now each and every question that I will be discussing, I will be going through each and every problems. So the questions will be displayed in the screen and you can take a screenshot of that for if you just wish, or if you can directly buy that book Himanshu Pandey as well, or else you can just take a screenshot of the problem and then just see how we can solve it. So the first question is given on your screen. Here you can see that there is a structure given, drawn like this way. Just let me draw this structure first. So this is the structure. Now they have asked that there are these protons are present over there. So they have been asking that which of the indicated hydrogen in the following is the most acidic one. Now the protons we have like this one, this one, this one, or this one. These are the things. Now you see, as we all know that for the acidity we need to see that the stability of the conjugate base, right? So if we just want to see the stability of the conjugate base, let's say for this one, if we have a negative charge over here, then what will happen? This negative charge, if it is present over here, for example like this way, this negative charge is only stabilized by the minus I effect of this nitrogen. That means here we have the minus I effect only. Here if we just make this proton out, so here it will be the electrons present over here, and those electrons will be stabilized by this resonance. So here resonance is a parameter. Here inductive effect is the parameter, here resonance is the parameter. Here you see there is no such parameter present over here if there is a negative charge. As you know that this is only the carbon, there is no alpha positions, so there is no scope for resonance, no scope for inductive effect as well. So this is unstable completely. Now here you see if we have this proton out, for example like this way, so here we will be having a negative charge like this way. So this can take part in resonance, as well as this negative charge will be stabilized by the nitrogen atom, as this nitrogen have a minus I effect as well. So here minus I and minus resonating parameter both are actually present. So in this case inductive effect only, here is only resonance, here is no stability, here is resonance stability as well as minus I stability. Hence your answer will be that this proton is highly acidic than the rest. I think this is clear to you. So we will quickly proceed towards our next problem. The next problem it says that in which of the following compounds is hydroxylic proton the most stable. Now here you can see for the problem A, I am just writing the basic structure and then afterwards I am just changing it. Here is 1, 2, 3, 4 OH. For option A there is one fluorine here, is option 1, and in option 2 there is one iodine here, is option 2. Option 3 is the fluorine present over here, and option 4 the fluorine is present over here. Now among all of these 4 you see that it has been telling about the which of the proton will be most acid. That means this proton will be acidic. Now here you can see that this proton has been, the electron density from the proton has been extracted by this oxygen present over here. So it is delta minus, this is delta plus. Now this delta minus is more stabilized by the inductive effect of the halogens present over the side chain, right? So here you can see, if this is actually what we call about the electromagnetic effect or the inductive effect. Now inductive effect in our previous classes as well we have seen that is only present as the most nearest atom is present over there, which means this fluorine can directly uptake the electron density from here, and this can stabilize easily that proton or the negative charge over there, del negative. This one is far away from this one is more far away, and this one is even more far away. So hence your answer will be that this fluorinating agent or this fluorine containing compound, that is the option D, will be the correct answer. Now quickly moving towards our next problem, that which of the following pairs does not represent resonating contributors to the same species? Now here you can see one thing, that does not represent the resonance contributors of the same species. That means the most stabilized form, you need to find it out. Now for example, if we just want to see that, and which is actually does not represent, that is very important, which does not represent. Now you can see there are 4 options. Quickly, just without anything thinking, you can easily tell in the option D parameter that here it is CH3 and nitrogen dioxide, this one is plus, and they are telling the option is this one. Now you know that pentavalent nitrogen is most unstable, or it is very much rarest to find. So that means this is the wrong part or the wrong resonating structure. As you know, if this one gets negative or if this electron gets into the resonance, then this one should get out. Hence the last option will be the correct answer for this particular problem. If this is fine, then we need to proceed towards our 4th problem. It's given in your book that which of the following is not a planar molecule? Without seeing anything, you can easily find it out with the first, that is the option A, because this is an alene system. We have already discussed that it is CH2 double bond C double bond CH2. We know how this is not planar or non-planar. So this one, there is a plane like this going like this, and there is another plane which is going like this. So this is a non-planar molecule or non-coplanar molecule. Hence this option A will be correct in this case. The next problem, you can see that question number 5 it is. So which of the following pairs does not represent the resonating structures? Now in the first point, you can see that 5A, it is given that it's actually a cyanate molecule, and the first one is absolutely correct because it actually removing the electron and just letting you see such that you can understand the problem very well. For example, this CH3 C triple bond N double bonded single bonded O. This is the structure. Now if this electron has been pulled up by this nitrogen via resonance, then you can find this structure very well. CH3 C double bonded N single bonded O, and here it will be plus. So this is fine. Next it is CH3 N O minus double bonded. This one is, I guess, CH2. Yes, CH2 like this, and this one is positive. It's very simple. This one will come back and this one can go out. So that means the option 2 is also correct one, as we can see from here. Now let's proceed towards the option C. As we can see, the option C, it says like this way that it is diazomethane molecule, CH2 double bonded N, this one is plus, this one is minus. So of course this can happen, this can form a double bond over here, triple bond over here, and this can get minus. So the answer will be CH2 single bonded N, triple bonded N, this one will be plus, this one will be minus. This is the structure of diazomethane we have already discussed. Now the fourth point is this, that it is the phenyl ring, phenyl C double bonded O single bonded NH3 plus. Now here you can see there is no such possibility such that the pH C double bonded O and single H can form this thing. This is actually a proton shift. Like here, this proton is shifting over here. And this is a part of tautomerism. It is not a part of the case of resonance. So hence, this option D will be your correct answer in this case. Now quickly moving towards the next problem. It is the in which of the following pairs is the structure on the right that is the major resonance contributor. Now in the first case you can see, now here it is given the major resonance contributor. Now in case of the option A, you can see that the molecule has only one resonating character, only one molecule. That's actually the resonating structure, the canonical structure, and there is no such other scopes for the resonance. For option B as well, you can see there is no other scope of resonance. It's actually uptaking the or having the resonance in the same. But in case of option C, you can see that this one is actually the structure. So if this one gets minus, so this one will form a O minus and C plus. Now you see this one is an aromatic part. Aromatic stability is there. Again the resonating stability is also there. So this one will be your correct answer, as this one gives you the major resonating contributor. I think this one is perfect and you can go through it very well. Now quickly moving towards our next problem. As you can see there is, in which of the following pairs of resonance contributors is the structures on the right is an important contributor. So all of the options that you can see over here, all of them are actually absolutely perfect and they are actually contributing the most. Hence the answer will be all of the above. Now in case of the next problem, it is given that examine the following resonating structures of formic acid and arrange them in the decreasing order of stability. So let's draw the structures first. Hydrogen, C double bonded O, OH, H, C, O minus, double bonded OH, H, C, single bonded O minus, plus OH, and H, C, single bonded O minus, OH minus. Now if we can see that these are all of the possibilities of resonating structures, then you can see that we have already discussed that non-charged molecules or the uncharged molecules are more stable than the rest. So this one will be your first priority. Next, all of those are resonating structures, but here you can see the number of covalent bonds. The number of covalent bond is highest over here. Hence this one will be the next one. And between all of those, electronegative is having a negative charge and electropositive comparatively having a positive charge. And the next, this one will be the number 3 and this one will be the number 4. So this will be the correct order of stability in this case. So one of the things that is most important in this problem that we have already seen, that number of covalent bonds, it should be your first priority. Before that, if a molecule is charged or uncharged, so charged molecules, those will be unstable comparatively towards the uncharged ones. And of course, for that, if you need to understand it very well, then you have to go through in my last lecture class. It will be there present, where we have discussed the stability of all of those structures. Now the next problem is, which of the following compounds will not show resonance? Will not show resonance. Now see, in the first case you have like this sort of moiety, CH2 plus. Here you can see the resonance is feasible. Planar molecule. After that you can see that CH2 double bonded CH, single bond CH, double bonded CH, and then CH2 plus. So this can shift, this one can shift, so resonance is possible. Option number 3, here is nitrogen is having a NH3 plus. Here this one is not possible because nitrogen is incapable of having a pentavalency. So this one cannot form any resonance. And option D, of course, it can form a resonance. We have already discussed it in our previous class. You can go through from there. So here the option C will be the correct one. I guess you can go through it very well. So the next problem is, which of the following compounds will exhibit d orbital resonance? Now you see the d orbital resonance is very important, that the d orbital will be used to and accustomed with all of these things such that it can be in a part of the resonance. Option A, they don't have, it is the OH, the phenol. OH doesn't have any sort of d orbital, so we will be cancelling out. Option C, chlorine has a d orbital. Option B is there. So here you can see the pentavalency will enact. The phosphine is present over here. So here you can say like this sort of resonance can take place. So of course this can have a d orbital resonance, except the chlorine. Chlorine, they usually donate the electrons from the other orbitals, but not the d. And the last option is also they don't have any sort of d orbital. Hence option B will be your correct answer. Now moving into the next problem, it says that which of the following represent resonating structures of biphenyl system. Now you see, it is the biphenyl system is actually shown like this way in the problem. So in each and every case, you can see that this may happen like this one can come over here, this one can be minus. So option A will be correct. All of the molecules can change, so option B will be correct. And each and everything can also take part in the resonance, so option C will be correct. Hence the option D will be the correct one, that all of those are correct resonating structures. Now moving into the problem number 12. So which of the following is not a permissible resonating form? That means which is actually a not resonating form. I guess I don't need to tell anything regarding this because I have already discussed the overall problem. The option C, you can just make it sure that the option C will be the correct one, because it's CH2 double bonded N, double bonded O, single bonded CH3 and plus, and nitrogen cannot have a pentavalency, it's not feasible. So your option C will be the correct one. I guess this is clear to you, all of you. Next, it is the next problem is the less contributing structure of nitroethane, ethene molecule, the less contributing one. Of course, you can see that all of those are very much important. Like the first structure, it's of course the most contributing because the number of covalent bond is the most. Option B, there is also the number of covalent bonds is increased. However, all those resonating structures, that is the electronegative atoms, are having a negative charge on its own. And of course, the less contributing will be the option C, because you can see that here no resonance is taking part between the nitrogen moiety, but only the ethene part is undergoing this reaction. So the 13, your correct answer will be option number C. Then you can move to, we will be moving towards the next problem, the less stable resonating structures. So the less stable is the first point that we have already discussed, that less stables we need to find out that whether the molecule is having the number of covalent bonds. So if the number of covalent bonds are higher, then the stability will be more. If we cannot tell, or if we cannot see that whether the stability is there or not, then we need to focus on the next part, that is the electronegative atom having a negative charge, electropositive atom having a positive charge. So in this case, your option A will be the correct one. You can easily check it out and let me know if you cannot check it out by your own. The next problem is which will be the least stable resonating structure. that you can easily go through that number of covalent bonds. In case of option A, B, C and D, of course you can see that the option C, they have the least, and of course here is only the thing that the aromaticity is getting broken without any sort of external stability, hence the option C will be your correct one. Coming to the next problem is actually showing that which of the following pairs of structures is not a pair of resonating structure. So we need to discuss it about. For example, first one is hydrogen, carbon, triple bond, NH. This one is plus. So automatically this can happen that this can pull out the electron and you can find the structure. Okay. Option B, it's having CH3, CH, double bonded CH, single bond, CH3. Now they are telling that the resonating structure is CH3, CH2, CH, double bonded CH2. Now this double bond from here, it cannot shift to there. This is a part of isomerism, not a part of resonance. So option B will be the correct answer in this case. So quickly moving towards our next problem, that's which of the following pairs of structures does not represent the resonating structures. Of course, that you can easily see without just taking a look into all of those answers. You can easily find that option number A, it's a part of hyperconjugation, CH3 C double bonded O CH3, and they are telling that the resonating structure is CH2 double bonded C O minus CH3. We have discussed this everything. So this is a part of hyperconjugation and not a part of resonance. So this one will be your correct answer. Now moving towards the next problem. That the most stable resonating structures are para-nitrosobenzene, the most stable structure. You can see in each and every case, we have to first find out the number of covalent bonds, and you can see all of them have the equal number of covalent bonds. So next, the electropositive element having positive charge, electronegative element having negative charge. If you compare, then you can see that in case of option A, there is carbon is electropositive, nitrogen is electronegative, and again oxygen is electronegative. Okay. In case of B, carbon is electronegative and nitrogen, both of the two nitrogens are electropositive and one oxygen is negative. That means option B will be not the answer. Option C, you can see that both nitrogens are plus and both oxygens are minus. That means here you can see only the balance between the cations and anions, hence this will be your answer of this problem. Coming into the next part, that which of the following molecules has the longest C double bonded C bond?